2.7 is another section that I would really consider a kind of a review section. I know you've seen this somewhere before, like probably in an algebra class or even in high school. But this section is looking at compositions. So in other words, what we have here is we have two functions, or we could even have more than two functions, but let's say we have functions f of x and g of x. And my goal is to find, this would be read f of g of x, okay? Or you could read that f composed with g of x. So that open circle in the middle there, that means the composition, and then the input variable is x. Well, in any case, what I can do is I can look at the inner function. So you see the g function is the function closest to x. That means that's the function I'll apply first. Then I'm going to put that result into the function f of x, okay? So actually, what I have here is I actually have two different ways of writing the same thing. I can write this or I can write that. Okay, those are the same thing written in a different way. This is the way we typically write a composition. Okay, so now I'm going to take the g of x function and I'm going to substitute that in to the f of x function. So that means wherever I see the x's here, I'm going to replace those with that g of x. So this is going to look kind of fancy. Let's see. So the template for f of x is what? Something plus a 1, something minus a 4. So what is the input? Well, the input is actually that whole rational function, g of x. Okay, now I just have to simplify this. So I'm going to use that trick where I multiply by that denominator, by that LCD. So I'm going to multiply by that top and bottom. Okay, so there, the denominator cancels. That's why this trick works, right? But here, there's nothing to cancel. So that 1 stays attached to the negative x minus 2. My denominator cancels. 2x minus 3. Here, nothing to cancel. So the minus 4 stays attached to the negative x minus 2. Distribute those coefficients and combine the like terms. Make sure I got all that right. Okay, looks like it. So what are my like terms? Let's see, 2x minus x, x minus 5. 6x plus 5. Okay, so what is this? This is my f of g of x, my composition of the functions f and g. Okay, so what are some things I could do with that? Well, let me do something first. Let me get the domain of that. That's one thing I could look at. Okay, so what I have here is I have a fraction. So remember, if I have a fraction, the bottom of that fraction cannot equal 0, right? Because I cannot divide by 0. So x is not negative 5/6. Okay, so I'd say the set of all the x's where x is not negative 5/6. But why am I leaving a space here? Well, so if I was just given this, I mean, if I was just given this, really, and this was a function, say this was a function like h of x, and they said, find the domain of h of x. Well, actually, then I'd be done. That would be the domain. But I have to be careful, because how did I get this result? Well, I got this result by computing f of g of x. So if you look back at the intermediate steps here, I would not have been able to get that answer if this step would have been undefined. It would have been impossible to get to that result. So that means that I also have to look at this denominator. Okay, so I also have to say negative x minus 2 is not 0. X is not negative 2. Okay, so I actually have two values of x that I have to exclude from the domain. So generally speaking, I'm looking in two places. So I got this from looking at the result, like looking at the answer here, okay? I got this, I could say this one in really two ways. By looking at the intermediate step. It's kind of the way I just explained it. So I said, look at the step here. I never would have been able to get the final answer if that step would have been undefined. Or I could say, look at the inner function. That would work as well. Because you see how this is the inner function, the g of x. Okay, so that function is the one that would be undefined if x were equal to negative 2. So I could really look either at the intermediate step or back up at the inner function. Either way, it's going to give me the same exclusion. Okay. All right, so anyway, well, let's see, what else can I do? So that is the domain, and that one is set builder notation. Okay, so remember this was called set builder notation. So I could also write that domain in interval notation. So for that, I think it's kind of helpful to think for a second just about a number line. Okay, let's see. Here's negative 2. Here's negative 5/6. So what I really want to say is the domain is everything except for those two values. So you see here I'll actually have 3 intervals I have to account for. So the other way of writing the domain would write negative infinity to negative 2, union negative 2 to negative 5/6, union negative 5/6 to infinity. Okay, so let's see, this is my domain written in set builder notation. This is my domain written in interval notation. Okay, and what are these the domains of? Well, these are the domains of f of g of x. It's right here, okay? So what if I wanted to compute, say a numeric value? Let me give you a couple options. I'm going to kind of clean this up, I think, so we have a little bit more room. So I'm kind of thinking, well, what if I wanted to know, like, f of g of 1? Well, I have a couple ideas. so what about find f of g of 1? Okay, so kind of the most basic idea would be to do this just like I did the composition with the variable x. So I could say, all right, well, first I'd find g of 1, then I'd plug that in f. Okay, so what's g of 1? That'd be 2 times 1 minus 3 over negative 1 minus 2, negative 1 over negative 3. Now I have to find f of 1/3. Trying to move this down, see if that works. Okay, so now I have to take this result, right, and plug this into the f function. That's what we're doing here. So now I'm finding f of 1/3, so that'd be 1/3 plus 1 over 1/3 minus 4. And we multiply this by 3 over 3, so that'd be 1 plus 3 over 1 minus 12, 4 over negative 11. Okay, so I got that composition, but I had a fair amount of work to do. I had to first find g of 1, then I had to take that result, plug it in f, and then do this calculation. Okay, then I got my final answer, which is the negative 4 over 11. Okay, so this is my f of g of 1, which is what I wanted. But here's my other idea. So you see how down here, we actually found the f of g of x function? I don't know, do I want to clean this up as well? Maybe so. So another way I could find f of g of 1 would be, well, couldn't I use this composition that I found for f of g of x? And so what would I do? Well, wouldn't I just plug 1 into that composite function? Okay, so let me try it that way. So, or f of g of 1 would be 1 minus 5 over 6 plus 5. Oh, that's a lot faster. Did I get the same answer? Yes. Okay, so say I wanted to do a bunch of these numeric calculations, f of g of 1, f of g of negative 1, etc., etc. Well, then it would be really useful to have this, this nice composite function so that I could just plug those values in and do that calculation in just one step. Okay, so I can actually do these compositions in any order. So say I have these same functions, and I want to find, instead of f of g, I want to find g of f. So where are the functions? Let me maybe copy those so we can refer to them below here, at least to set it up. Okay, there are those functions. So this time, the inner function is f. That's the one closest to g, or closest to the variable x. Okay, now g is the outer function. Okay, so now I'm taking the f of x function, plugging that in to the g of x function. So the g of x template looks something like this. Okay, then I'm putting f in there. So I have x plus 1 over x minus 4 in both those bubbles. Okay, then I do my calculating. Get rid of these. So I'm going to multiply this top and bottom by that LCD. Okay, so here I cancel that x minus 4 in the denominator. So I'm left with a 2 by an x plus 1. Then the 3 has nothing to cancel. It stays attached to the x minus 4. On the bottom, cancel the x minus 4. So I have a negative x plus 1. But the 2 has nothing to cancel. Distribute. Okay, and then combine the like terms. So negative x plus 14, and then negative 3x plus 7. Okay, so I mean I could leave it like that, or I could multiply the whole top and bottom by negative 1. So that would be an equivalent answer. I could really write either of those. And so that's the g of f of x composition. Let me write the domain of that one. So remember, for the domain, I have to look in two places. At the result, I have to make sure the denominator there is not 0. Then I have to look at the inner function. That's the f of x function. So you see how in this step, I wouldn't have been able to do this calculation if x were equal to 4. So I have to exclude both of those values. That's my set builder notation. My interval notation would be negative infinity to 7/3, union 7/3 to 4, union 4 to infinity. Okay, now I could do f of f and g of g. I think I'll pick one. They're all very similar. Oh, I don't know. Let's do g of g. That's the harder one. So I'm going to copy g. Well, be good enough. We'll fix it when we get down here. So I'm going to skip f of f. They're all very similar. Let's do g of g. Okay, so there's that g function for reference. So now I'm actually taking g and plugging it into itself. So the template for g looks like this, right? But now I have to put that whole fraction back into each of these parentheses. Okay, and then I simplify. So now I'm going to multiply it by the negative x minus 2, top and bottom. Cancels. So I'm left with the 2 times the 2x minus 3. Now that 3, there's nothing to cancel, so this stays attached to that constant. Here it's going to cancel. Here it's not. So the denominator would look like this. Okay, distribute. Let's check all that. That looks okay. Okay, combine the like terms. What is that? 7x, oh, just 7x, okay, over 7. Oh, that's cool. This one comes out to be just x. So how about the domain of that? So when I'm looking at that, it looks like the domain is all real numbers because the denominator is 1. That function is actually never undefined. But don't forget, you have to look also at this intermediate step. So the domain of that composition is actually all the x's where x is not equal to -2 still. So here's another set of functions. We're going to do the same thing, finding those compositions. So here I actually have root functions, cube root and a 4th root. So let me go ahead and try f of g. So I'm taking this 4th root and substituting it in. So I guess I would have the cube root of the 4th root of x plus 1. So actually I cannot simplify this, and the reason why is because I have this sum in the middle here. So if you think about this, I mean, you could actually write this in terms of fractional exponents instead of radicals, right? You see how that's like if I have like x plus 5 squared. I cannot distribute the 2 like that, right? Instead, I have to take that x plus 5 and multiply it by itself with FOIL. So whenever I have a sum or a difference here underneath that exponent, I can't actually distribute. So actually I'm stuck. As far as my composition goes, I'm done. Doesn't simplify. So actually that part was really easy. So maybe the more interesting part with these will be finding the domain. So for that, I have to think about radicals for a second. So domain of radicals. We'll do a little side note here. So what if I have a root with an even index? Okay, so the first one of those would be square root, then there's 4th root. Okay, I could have any even index, the 18th root. So in that case, if I have an even index root, whatever it is that's underneath that root cannot be negative. It has to be greater than or equal to 0. What about a root with an odd index? Be like cube root, 5th root, 131st root. Well, actually, think about like cube root. Cube root of -8 is defined. It's -2. I can take the cube root of +8. It's 2. What's the cube root of 0? It's 0. Actually, roots with odd indexes are defined for all real numbers. So with the odd index root, I actually don't have any restrictions on domain. Okay. So I really only have to be concerned about roots with an even index. So when I'm looking back up here at my composition, well, I have that 4th root. So whatever is underneath that 4th root, and that in this case that's just x, has to be greater than or equal to 0. So I'll say the set of all x, where x is greater than or equal to 0, or in interval notation, I would write it like so. Now I have a cube root here, but actually remember the cube root, the domain of that is all real numbers. So it's only that 4th root that I have to be concerned about the domain. Okay, so I'm going to do g of f. what are we doing here? We're taking the f function, plugging it in the g. Okay, so this is going to be the fourth root of the cube root of x plus 1. Okay, now this one, can I simplify it? Think about fractional exponents. This is what I have here. So this is like if I have power to a power, I multiply the exponents, right? So actually this one, I multiply straight across. So this one turns into the 12th root of x plus 1. So that I was able to simplify. Let's find its domain. Okay, what about the domain of this one? So here I have a 12th root. So whatever's underneath that even index root has to be non-negative. So I'd say the set of all the x's where x is greater or equal to -1, or I'd say in interval notation, -1 to infinity. That was scratch work there. What about f of f? So there I'd be taking the cube root function and plugging it into itself. So that'd be one where I can't simplify, because you see how I have the sum separating terms underneath each of these roots? So it'd actually be stuck. And then I guess this is the easy one, because I only have cube roots, odd index roots here. So actually I'd say the domain is the set of all x's where x belongs to the set of real numbers, or in other words, x is any number, any real number, from -infinity to infinity. And one more, g of g. So g is the fourth root of x. Okay, so if I plug that into itself, that's the fourth root of the fourth root of x. So that's like x to the 1/4 to the 1/4. X to the 1/16, the 16th root of x. So that's an easy one too. And the domain, well, that's an even index root. So I must say what's underneath that root is non-negative. See what the next one is. Example 4. Okay, so more root functions. But here we're looking, find the domain of f of g. Okay, well, let me go ahead and find f of g. Why not? So f of g of x is square root of x minus 3 minus 2. Now there I'm stuck, because I have a subtraction here, a subtraction here. Nothing I can do with those. But I'm interested in the domain. Okay. Well, see, I have two issues. So here I have x minus 3 is under a root. So that says x is greater than or equal to 3. But be careful, because look at this. Isn't all of this still under a root? Okay, so if I were to just say the domain is x is greater than or equal to 3, that means if I was to take a number like 4 and plug it in this function, look what would happen. I'd have 4 minus 3, that'd be square root of 1 is 1 minus 2. I'd have the square root of a negative still. It'd still be undefined. right? So that's because I don't just have to look at what's under this root, but I have to look at what's under this square root as well. So wouldn't it also have to be true that this quantity has to be non-negative? So x would actually have to be greater than or equal to 7. Okay, so who wins? So I mean, this has to be true and this has to be true. But if you think about what that's saying, I'm saying x has to be bigger than or equal to 3. Here's 3. But it also has to be bigger than or equal to 7. So in what region would both of those things be true? Just this one. So this guy wins, right? If x is greater than or equal to 7, it's automatically going to be greater than or equal to 3. So when I write the domain of this, I would really just be writing this, right? Because that would account for x also being greater or equal to 3. Okay, what's left? Can you find functions f of x and g of x such that the composition of f and g is this function big F? So the idea here is, can I find functions little f and little g so that when I compose those together, I get that result? Okay, so if you look at the order here, let's see, g of x is the inner function. So this should be the inner. This should be the outer. So with these, there are really multiple options. My thought is, well, I just kind of look at the composition. I say, what really looks like it's the inner piece? And my first thought is to choose 2x plus 1 as the inner piece. Then I'd say, what would I have to do to 2x plus 1 to get back this composition? Well, I'd have to raise it to the power 6, right? If you think about actually doing the composition, I would take this and substitute it in here, and I would arrive here. Okay, so I found a set of functions that I would compose together to get that result. Okay, what about this one? Same thing. My inner, my outer. This one I have a couple ideas. What if I choose this to be the inner piece? Then would this work for the outer piece? So then I would plug this in here, subtract 4, and I'd have that. Looks good. This one I have another idea. What do you think if I let the inner piece be the square root of x plus 3? Then I just take that quantity and subtract 4. Either of those would work. Either or. Let me ask you what you think about one other thought. So do you think this would work? What if I said this? What if I just said the inner function is x? Then the outer function would be root x plus 3 might just be that composition itself. So that actually, I mean, technically speaking, if I replace x with x, I mean, that gives me the correct composition, but it's kind of like cheating the question, right? I didn't do anything interesting. So usually what we do to prevent you from doing this would not be an acceptable answer. And so what we usually do to prevent you from doing this is we add something in the instructions that says, find non-identity functions, f of x and g of x. That means one of the functions cannot simply be equal to x itself. So find non-identity functions means I have to find interesting functions. Not something like that, because actually g of x here is the identity. Y is identical to x there. Okay. So what about a couple more? So you're really just kind of looking at these and kind of just taking a guess and then plugging it in, seeing if it works. So what if I try x to the 5th for the inner function? Then I'd have that quantity over that quantity minus 2. So if I calculated the composition, I'd plug this in here and here, and I'd have that. Looks good. Number 4 is the same thing, except there's one extra stipulation here. So here, we have to find functions f and g that we compute together to get this result. But whatever function we choose for g, it must be true that g of 4 is equal to 2. So I kind of just try something. So I don't know. First thing I think is maybe the inner piece is that root x plus 1, then the outer piece would be 3 root of that quantity. Okay, that would give me the right composition. But what about this condition? So if I find g of 4, oh, that's 7. That is not 2. So this quantity, this set of functions gives me the right composition, but does not satisfy the second condition. Okay, so that means I have to try something else. It doesn't work. Okay, so what's another idea? Well, g of 4 equals 2 kind of makes me think, well, what if g were the square root of x? Because the square root of 4 is 2. That would satisfy this then. So then I just have to figure out, well, what would the outer function have to be to give me that composition? Well, let's see, I'd have to have a 3 in front, because I'd have to have a square root, then an x. How do I get x from square root of x? Wouldn't that be the square root squared? Look at what happens if you plug that in. Does it work? F of g would be 3. Then you'd replace x with root x. You'd have root x squared. That'd be 3 root of root x plus 1. Oh, look at that. I got it. So again, you kind of just have to try things with these until you get something that works. I need to box these. Okay, find functions f of g, find functions, let me try that again, find functions f of x, g of x, and h of x, such that the triple composition f of g of h of x is f of x. This is the same thing, except I actually have to find 3 functions. Actually, I think these are even easier. Look at the order. H is the innermost, G is in the middle, F is the outer. So if you look at this composition, here's the way I think about these. I think about if I were going to plug a number in there, like 4, what would the first thing I would do to that number 4 be? I would take the square root, right? So my innermost function would be the square root of x. So then I would have the square root of 4, that'd be 2. What would I do with that next? I'd take that and I would subtract 5, right? So I'd take that quantity and subtract 5. Once I had done that, the last thing I would do would be now I would take that quantity and I would cube it. Okay, think about if this would work. I'd take this, plug it in here. Then I'd take this, plug it in here. Okay, look at that, works. So like I said, I think these triple compositions are actually even easier. Okay, let's do one more of those. Okay, so if I was to take a number and plug it in there, first thing I would do to that number is raise it to the power 6. Then I take that quantity and add 2. After that, I would take the cube root. So this would go here. Then this would go here. And I get that. That looks good. And I think that's everything.